Okay, so in the previous video, we sort of suggested that we can describe the full time-dependent wave function as a sum over the different psi n's that looks like this, with the space and time parts separate. And now we want to show that this is not quite right. And so we want to correct this expression. And we'll do it by imagining that we choose psi of x and t. Right? We want some dynamics as well. So we're going to choose n equals 1 to 2. So we'll have two of these. So we'll have psi 1 of x, e to the minus I e1t over h bar, plus psi 2 of x, e to the minus e to the minus I e2 t over h bar. And we know that each psi n is square root of 2 over L, sine of n pi x over L, and so this would look like square root of 2 over L, sine of pi x over L, e to the minus e1t over h bar, plus same normalization factor for psi 2, but sine of 2 pi x over L, e to the minus I e2 t over h bar. And we know that if we integrate from 0 to L, psi star of x and t, psi of x and t in dx, this needs to be equal to 1. And we'll now show that we will not get this. And so we will correct this expression. But we'll be able to get there by understanding what we did wrong. So let's find psi star and multiply it by psi, and let's integrate that. So this becomes what? An integral from 0 to L of, remember what psi star is, that changes this, right? We want the complex conjugate, so this becomes e to the I e1t over h bar, and this becomes e to the I e2t over h bar. And so we have to multiply that by psi, which is this function here. And therefore, we end up getting, 2 over L, because we square the square root of 2 over L. We have sine squared of pi x over L, and a term that squares the 2 pi x over L, right? So we multiply this by the version of this that's in the complex conjugate, and the time-dependent parts give us 1, because we have e to the minus I e1 and e to the I e1 terms. And so they give us e to the 0, which is 1. So we have these two terms, plus we have cross terms. Right, so the cross terms look like 2 over L times the sine of pi x over L sine of 2 pi x over L. And we have e to the I e1 minus e2 t over h bar. That's one cross term, plus the other one with the same factor here in front, 2 over L, of course, sine of pi x over L sine of 2 pi x over L, e to the I, where we flip the two terms, the two energies. Okay, so that's what we get, and this integrates in dx, and it would be a little strange, actually it would be very strange if the time-dependent part, if this calculation depended on time, because that would mean that the normalization condition depended on time, and that better not be the case. So let's integrate this, but let's look at these terms. These are the terms that we integrated before. We said that 2 over L sine squared of n pi x over L n dx, all of those functions give us the same quantity. The integral was independent of n, so all of these give us 1. So we get 1 from this one. The same is true here. And notice that these two terms vanish because of orthonormality, right? Sine pi x over L and sine 2 pi x over L. This is the condition psi m star psi n in dx over the entire range. This must be equal to 0 by orthonormality. And so those last terms give us 0, but this is already too large, and we get 2. And so the idea here is to recognize that if each individual psi n x e to the minus I e n t over h bar is normalized, then we have to weigh these wave-like solutions. And so our more general solution has to require a weight for each wave. And so we need an additional number. This could be a complex number, psi n x e to the minus I e n t over h bar. So this is the solution that we're looking for, and we can understand this as a weighted sum of waves or wave-like objects.